going to show you one more. It's still called method 2. Sorry about that. But it's going to take account for the changes. We're going to start off with the force of attraction between the middle guy and the girl on the right. We're going to start off with that force of attraction, and then we're going to multiply it by a factor that accounts for the switches to the information for the guy on the left. So we're going to say what we had that still works is all the information for the girl, and we're going to switch whatever information we had for the guy in the middle over to information for guy on the left. So here's what that factor should look like. Again, the oh, I messed up and I put mass of the guy on the left. I meant mass of the girl on the right here. Sorry about that. So her mass is not changing but what we had before was the mass of the guy in the middle, and now we're substituting in for it the mass of the guy on the left. And we had the distance between the center of the girl on the right and the guy in the middle, and now we have the distance between the center of the girl on the right and the guy on the left. So and by the way, the gravity constant cancels out. So here we have 182 over 95, the after divided by the before for the mass, and 4 divided by 2 for the distance, and that whole number is going to get squared. That complete number is going to get squared down there because it's representing the distances. So it had been 2 meters between middle guy and the girl on the right, and now it's 4 meters between the left guy and the girl on the right. So that factor, when you put it in, becomes 0.4789. Multiply that by the force of attraction there had been between the guy in the middle and the girl on the right, and you get again 3.79 times 10 to the minus 8 newtons. My point in showing you these methods is that a common type of problem that's given for this kind of for this unit involves just taking into account the changes between situation 1 and situation 2 and figuring out the factor by which you could multiply the force that was observed in situation 1 in order to figure out what is the force in situation 2. Alright, I'm going to switch gears here and talk about something else. Galileo is there is a story that has been reported concerning Galileo, saying that he challenged philosophers of his day with this thought challenge. He said, if I drop an object that's large with a large mass and something that's small with a small mass from the same height at the same time, which one should hit the ground first? And the philosophers seem to think that the one with the bigger mass should hit the ground first. And they thought that because if they held them in their hands, they could tell that the one with the bigger mass was being pulled down stronger. And this makes sense. According to Newton's law of gravity, the bigger the mass of that object, okay, of course the mass of the Earth is constant here, right? But the bigger the mass of the object, the stronger the force of attraction between the Earth and the object. So this makes sense. If you put a bowling ball on a scale, it'll read a bigger weight, a bigger force, than if you put a golf ball on a scale. Alright, now by the way, the mass of Earth is huge. It's around 6 times 10 to the 24th kilograms. And the distance from the center of the Earth, remember this is distance between centers, the distance from the center of the Earth to the surface is around 6,378,000 meters, which is huge. So adding the distance to some height above Earth or to the center of a bowling ball, the center of a golf ball, is not changing this number of meters appreciably. So we just usually leave it right there at 6.378 times 10 to the 6 meters. In any case, I want to point out that the reason this drawing looks as it does is because supposedly Galileo then performed the experiment in front of these philosophers, dropped two things of different masses but similar densities, I'll mention, from the Leaning Tower of Pisa, and they indeed hit the ground at the same time, which should have blown the mind of the philosophers. Well, I want to talk about why that should be. Why should they hit the ground at the same time? Well, let me say, how about we go back to Newton's second law and say that force equals the mass times the acceleration of an object, and in this case we're talking about the acceleration due to gravity. The mass times acceleration due to gravity is if that multiplies out to the force of gravitational attraction, right? And Newton's universal law of gravity gives us a formula for calculating that force of gravitational attraction. So here we go. The universal gravitational constant multiplied by the mass of the Earth multiplied by the mass of the object divided by their distance, the distance between their centers squared, and that's going to be really close to the radius of Earth, by the way. Okay, all of that together equals the force of gravitational attraction of the Earth for the object, right? And I hope we've just stated that's equal to the mass of that object multiplied by gravity's acceleration of that object. There's an interesting thing you can see here then. The mass of the object simply cancels out. Notice, if the mass of the object gets bigger, the force that gravity exerts is bigger. If the mass of the object is smaller, if we talk about a golf ball instead of a bowling ball, then the force that gravity exerts is directly and proportionally smaller. So it doesn't matter in this case what is the mass of the object. It could have been, a several ton satellite. It could have been a bowling ball, a golf ball. Gravity's going to accelerate it. If it's at the same distance, it's going to give it the same acceleration. That's going to have some great implications for us. Okay, someone has asked, and it's a good question, how can we estimate the mass of a planet or a star? By the way, I'll just point out that this planetary motion we have sort of animated here is supposed to be matching some of Kepler's laws, elliptical, moving faster as it gets closer to the star. Let's say let's say that gray object is a planet rotating in its orbit around a star. Remember, Kepler's laws say the orbits are elliptical, and that as the planet moves along its orbital path, it sweeps out equal areas, sectors of equal area in the same amount of time, which means it's going faster when it's closer to the star and slower when it's further away. In any case, someone asked, how can we estimate the mass of a planet or star? And here's your answer. Since the gravitational acceleration is the same for any object, that's what we just showed on the previous slide, right? We showed, in this case, you might be thinking the mass of the sun or a star here. If you talk about the distance at a certain position removed from the center, a certain position away from the center of the sun, and put in the universal gravitational constant, no matter what the mass of the other object is, its acceleration, its gravitational acceleration is going to be the same. So that's what we're saying here. Since the gravitational acceleration is the same for any object, and that means at the same distance, if we can estimate the radius and the period, that means how long it takes to go all the way around once in its orbital path, we can estimate the mass of the star or planet. Why is this? It's because what is keeping the planet on its roughly circular path? What is providing the centripetal acceleration, or the pull toward the center of that path? It is gravity itself. Well, if we know the radius, the average radius of that orbital path, and we know how long it takes to traverse that path, then we can figure out the tangential velocity of the object going around the distant star, let's say. And if we can figure out the tangential velocity and we know the radius, then we can take the velocity squared divided by the radius and find the centripetal acceleration, which is due to gravity. So regardless of the mass of this planet orbiting, regardless of the mass, if we know the radius and the period, we can figure out the gravitational acceleration. And that you can see from our previous equation. If we know the distance, which is the radius, and we know the and if we've calculated out the acceleration, we know the universal gravitational constant. The only unknown in this little equation is the mass of the larger object, say a star or a planet. The star with a planet orbiting it, or a planet with a moon orbiting it. There you have it. I'm glad someone asked that question. It's a really awesome application of this principle.